All right. So moving along. Everything you've learned so far, you're still going to use. Don't think chapter 7 is not going away. There's a reason this stuff is in chapter 8 and not chapter 6. So in chapter 6, we looked at volume of shapes when we were rotating it, stuff like that, and area under the curves. So, and most of those, depending on how complex the function was, you could do that with U substitution in the basic integration formulas. However, when you're getting into looking at arc length and surface area, you can a lot of times those end up falling into the place of using the trig integration, the trig substitution, and those type of rules. So we need to do that after chapter 7. So how do you find length of anything? Yeah. What's the distance formula?
I squared plus y squared, x square root of that.
Okay, kind of. That's close. That's close. No, it's close. It's kind of like the Pythagorean theorem. Why is this not writing? Why are you not writing? There we go. So that would be just the Pythagorean theorem if it was that. The expanded one would be x2 minus x1 squared plus y2 minus y1 squared, looking at the points. So, but really it's the change in x squared plus the change in y squared, and then the square root of that. So when we're looking at these, that works really well when you have a straight line or a linear equation. When we start to look at a curve, we have multiple lines that we have to look at. So this is where calculus comes into play, because calculus allows us to say what happens when those 2 points right there become infinitely close together. Okay. So I've decided I'm not going to go through and do out the entire proof of this, because I honestly don't think it's going to help most people really understand what's going on with it. So that's the formula for arc length. So remember that dx is really the change in x. That's what dx stands for. So, and dy, or the change in y, is really the function. So you'd actually do a little bit of manipulation, but it ends up being the chain rule put into it. That's how you get the derivative of f of x in there. And then you factor out the dx, which is why that goes out in front. So these are the exact same formula. One is in Newton, one is in Leibniz.
Should I write both?
You can write whatever one you want. I am typically going to end up using the Leibniz notation when I'm writing them down, just because it flows better when we start to look at differential equations and stuff like that, dy dx. So you'll see me use that most often. I think it's easier to understand what you're doing instead of that little dash or the tilde there. So in essence, the arc length formula is we have to find the derivative of the function that we have, and then we plug it into the square root. Now you can start to see why we might need the trig substitution problems, because they dealt with the integration of roots. So that's where that comes into play. Sometimes we can get rid of the square root and we don't have to worry about it. Sometimes you can't, and we have to deal with it. So, all right. Everybody got this equation, these functions down? Okay, that's fine. Also notice that these are, the vast majority of the time, they will be definite integrals, because we are looking for an actual length. If you are looking for a formula so that you can find it for any part of the curve, it's typically from whatever point you want, and the second thing would be x. You'd actually put that as the x variable there, and then you plug back in afterwards. So it still would be a definite integral. It's just dealing with a variable as one of the endpoints. All right. Let's use it. So we're looking at the equation y squared equals x to the third. So let me actually graph it so you can see it.
Yeah, that's great.
So this is what y squared equals x to the third looks like. And we're looking at it from points 1, 1 to points 4, 8. So 1 is less than x is less than 4. And what was y? 1 to 28. So that's the curve we're looking for. We're looking for that length right there. It looks like a straight line. It is not quite a straight line. It's close, but it is not exactly a straight line. There is a little bit of a curve to that. When you're looking at, if you're plugging these into Desmos and you want to just look at the exact thing you're looking at, if you noticed here, this is how you put in your restrictions. So you put in your X restriction and your Y restriction for it. It'll actually just show you the piece that you want. So I got those from the points. The X went from 1 to 4 and the Y went from 1 to 8. So that gives me just the length of that piece that I want right there. So nice little thing to have an option for. All right. So we've got that. So my equation is y squared equals x to the third. It is not solved for y or x, so let's pick one we want to solve for. Let's solve for y. It's my life a little bit simpler in this case. So we're going to change y. So y ends up equaling x to the 3 halves because we did the square root of both sides. When I take the square root, what do I have to keep in mind? Positive and negatives. So if we looked at this graph before I put the restriction on it, you'll notice that I had both directions because I have the x and the positive and the negative version of that. However, since I'm looking at this in case of it's all on the positive side, I don't have to worry about the negative version of it. Okay. So I have the positive version of x plus, or x to the 3 halves. All right, so my arc length formula horrible dx. So the first thing I need to do this problem is I need to find my derivative of the function. So I need to find my dy dx. So what's the derivative of x to the 3 halves? Right, 3 halves x to the 1 half.
Can't wait till there's a really nasty function.
Oh, we'll do a couple. We're going to do some easy ones to get the concept of the actual problem down first before we do some crazy ones. All right. Everybody got that point? Make sense?
Yeah.
Okay. Now, when you're doing this problem, do not try to do the whole problem at once. Work underneath the square root first, and then deal with your square root. So if we notice this next piece that I have to do here is I need dy dx squared. So I'm going to square that. That becomes 9/4 x. Now I end up having 1 plus 9/4 x. Can I do anything with that? No. Okay, so now I can actually write my integral. Since I can't do any more simplification, we can write the integration. We're doing this in terms of x, so I'm going to use the x values of my points. So I'm looking from 1 to 4. All right. Everybody with me to there? Okay. How do we want to do this integral?
Trig sub.
Trig substitution is squares, right? But I don't have a square in this case. Yes. Yeah. What was the first thing I always say to try? Use substitution. Okay. So we're going to make u equal 1 plus 9/4 x. That means du equals 9/4 dx. So 4/9 du equals dx.
And that 4/9 comes out to
Yeah, that's you just pull that right out in front. You don't have to deal with it inside.
then we can do our
Okay. Now we do our integration. So it's the integral of u to the 1/2. Right. And then we have two-thirds u to the 3/2. So we have 4/9. So we have, what is it? 8/27. And then we can plug back in the 1 plus 9/4 x to the 3/2, and we're evaluating that from 1 to 4. Everybody good to there? Yeah, so now we're just going to plug the numbers in. So we have 8/27. We plug in 4. So we have 10 to the 3/2. And if we plug in 1, I have 13 over 4 to the 3/2.
why are we adding it?
Oh, it's not subtracting.
Okay.
I saw that plus. Yeah.
I just want to make sure.
Nope, you didn't.
We leave it like that.
And you can leave it like that.
So like,
The book makes a slight change to it, does it with the square roots, but it doesn't actually change the problem. So you can leave it like that. The only change that would end up happening is if this was an actual application style problem where you were looking for an actual length and stuff like that, you probably would just plug that and get a decimal answer out that would fit what you're looking at. So not every problem, like this works well for theory, but if you're going to turn around and tell the sheet metal person, yeah, I need 827, 10 of the inches of sheet metal, they're going to go, huh? So that's the thing. It's like when you're looking at the application style problems, which we're going to do towards the end of class, that's when you want to just get it as a decimal answer at that point. All right. So arc length formula, simple enough?
For now.
It doesn't like that's the calculus part of it. Like that's the understanding how to use the formula. Now it's just a matter of the more complex the actual problem gets, like the actual graph gets, the more complex the problems get. So. All right, let's look at this one. So what are we starting with in this one?
We should do it. Wow, I think.
Yeah. So we have x equals y squared. There's no point in changing it to the square root of x. We can leave it just like this. We do the integration in terms of y instead of in terms of x. So what's the dx dy? It's just 2y. So then I square that. Is 4y squared. So I can set up my integral now. What am I going from? Well, this one works out nice because they're the same numbers. I'm doing it in terms of y, so I'm looking at my y values. So it's 0 to 1. They were nice to you and made the same ones. Square root 1 plus 4y squared dy. No. Yes. This one we cannot use u substitution because I do not have a y in my problem to do the u substitution. So
Sorry.
oh, I'm like, you scared me. Like,
Ghost cough. Sorry. I thought it was on mute.
So we have to do those joining us remotely. We have to do, yeah. So we have to do trig substitution for this problem. This is the 1 plus the 4y squared, so we have to do trig sub. All right, so what is our substitution going to be? What's the one with the 1 plus or the plus?
A tangent of theta.
Yes. So we have, if we change this up, we have 1 squared plus 2y squared, right?
Yes.
So my tangent's going to be, so y is going to end up being 1/2 tangent theta.
Why? Oh, 1 over a.
Yeah.
I was definitely not going to.
All right, so dy is what? What's the derivative of 1/2 tangent theta? Nope, that's secant. Secant squared. All right, so these are definite integrals. All right, so let's change our intervals to thetas instead, so we don't have to go back to the dy and deal with my triangles. So if y is 0, what's theta going to be? Yes.
Sorry.
That's okay.
Why is y equals 1?
It's because there's a 4. There's the 2 is in front. Because we end up all right. So in essence, you're right. It's 2y equals 1 tangent theta. Divide by the 2. No problem. All right. So if y is 0, what's the value of tangents that's going to give you 0? Or theta that's going to give you 0 is 0. So if y is 0, theta is 0. If y is 1, we have to solve this. So I have 2 equals tangent theta. So the arctangent of 2 equals theta. I multiplied by 2. Get rid of the 1/2.
My brain's not
It's okay.
right here.
All right. So we have 0 to arctan of 2. 1 plus 1/2 tangent theta. Sorry. 2 times 1/2 tangent theta squared. I'm going to run out of room. I'm just going to run it out of this screen.
D theta.
Yeah, I'm going to run out of room. So I'm just going to run out of this screen. Brackets. 0, 2, 10, -1. Screw. Square root 1 plus 2, 1/2 tangent theta squared. And then it was 1/2 secant squared theta d theta. All right, let's clean up the inside of the square root part first. So the 1/2 in this, the 1/2 in this is going
Is
to.
all of that under the square root?
No,
It's
the
supposed
square
to
root ends right
be.
there.
Okay. All right.
Let's clean up this part first. So these two are going to cancel each other out, so I don't have to worry about that. I then end up getting 1 plus tangent squared theta, which is what?
1 squared.
What?
1/2 squared.
Right, but it's 2 squared too. The 2 and the 1/2 are both inside that square. So, because basically I replaced that y, so the 2 is there. So that's how I can cancel it out before I did the square. And what's the trig rule for 1 plus tangent squared theta? That's secant squared theta. And if I do the square root of that, that's just secant theta. So I have I can pull out the 1/2 from there, and I have 3 secant theta. So secant to the 3rd theta from 0 to arctan of 2 d theta.
That's a pretty nice number.
Oh, that's the problem. I thought you were showing us something. I was like, wait.
Oh yeah. All right. So, does anybody remember the integral for secant to the 3rd theta?
Everyone knows that,
Don't you know this one by the top of your head?
obviously.
We actually did this. Yeah, we actually did this in class.
Yeah, I know, that's why I'm going back.
It's in section 7.2.
I didn't. It's
Yeah.
something stupid.
I just moved it up front. The 1 plus tangent squared theta is secant squared theta. Okay. And then I took that secant theta and the secant squared theta to make secant to the 3rd
I
theta.
have 27 secant. Really good job.
Oh, it's it's this big old thing.
Oh,
Secant
Can't tangent.
theta
oh, I see it.
plus natural log.
Yes.
Secant plus tangent over 2.
So there you go.
C.
So here is the why mathematicians are lazy. If we've already done something, there's no point in doing it again. Okay. So if you, that's where like some of those ones where if we got the tangent square, we got the tangent theta, we got the secant thetas and stuff like that. It's like if you can remember those or have them written down that you can easily look them up, you don't have to redo that work because we've already done it. So that saves you some time. In this case, what it saved us doing was we had to do you have to do the trig integration ones in there, so you can actually change secant to 1 plus tangent squared, and then we do integration by parts. So it saved us a bunch of extra steps in there.
Why is there a random alpha in there?
Because the book, instead of writing that, wrote alpha.
Fantastic. I'm sorry, I don't know if I'm like super loud or
No, you're fine.
okay. I can't really hear.
So the book, instead of writing out arctangent on every one of them, they wrote the alpha there. So that right there is really just arctangent or arctangent of 2. All right. Now
We gotta plug in.
we got to plug all this in.
How? What's secant of inverse?
Okay, so let's actually work through this.
Can we just plug it into this one and call it again?
No. This one we're going to do out. All right, so we're going to, so to make my life easier, I'm going to use the alpha just because it's going to be a total pain in the butt to write this out if I don't use the alpha. So we have secant of alpha or A, tangent of A plus ln secant of A plus tangent of A. And if you plug in 0, tangent of 0 is 0, so that whole thing disappears. And secant of 0 is 1, so ln of 1 is 0, so that whole thing disappears. So you don't have to do the other side. Okay.
Feel like a dying apple.
And remember that A is arctangent of 2. So tangent of A is 2. Which helps me. That helps me out a lot. So all we really have to figure out is what secant of A is.
my x?
Well, let's look. So we've got secant squared of A is 1 plus tangent squared of A, right? That's the Pythagorean rule, right? Okay. So what's tangent squared of A? 4. So secant squared of A is 5.
Chilling.
Wait a minute. Let me write all this.
So secant of A is the square root of 5.
Oh, okay.
So you don't have to go through and do all these crazy things around arctangents, right? Use the rules that you know about trigonometry to help you, or the rules that you can look up really quickly about trigonometry to help you, because I doubt most of you have all these things memorized.
Yeah, no.
I know that.
Because 1 plus 4 is 5.
If it came to it,
Because tangent A is 2. 2 squared is 4. 1 plus 4 is 5.
if it really came to it, could I just plug it all with Desmos and get an answer?
You're gonna get a decimal. You're gonna get a decimal answer though, and this is gonna give me my exact answer. So now we can plug in what we know. So this one I have 2 times the square root of 5 plus ln 2 plus the square root of 5, and that's my final answer.
It's 2 plus 5.
Or square root of 5 plus 2. I don't like writing my square roots in the beginnings things, because if you don't necessarily know exactly where it ends, sometimes people continue to write it. So writing them at the end kind of eliminates that problem.
If you want to pretend, or because they make you distribute out that 1/4.
Yeah, they were.
Yeah, so you can get square root of 5 over 2 plus. It doesn't make a
Oh.
difference. It's literally the same thing. It all depends on, in essence, where you stop reducing is what are you going to use it for next. Since we're not using this for anything else, distributing the 1/4 really isn't helpful.
Even in algebra, I distributed it.
They were making sure you're practicing and understanding how to simplify things down, because sometimes you do want to simplify stuff down. So it's like, that's one of those things, like at this point, we're not using this for anything else. I'm sure you know how to multiply through the 1/4 if you need to, so I'm not worrying about that step at this point. I'm like, this problem, I'm making sure that you understand how to do the arc length formula, making sure that you understand how to actually solve out with the arctangents and stuff. That's something that most people don't do very often. So understanding how to do that is helpful. So especially when you're like, how are we doing secant of arctangent of 2? Well, you just work your way backwards from it. So, all right. Okay, let's. Just because I think this is actually a nice problem to do after the test problem that I gave you.
I kind of just gave up.
Oh no, it's gonna be.
All right. Okay, we're not using Simpson's rule. Set up my integral. And you can do it in terms of X or Y, it doesn't make a difference.
Okay.
It's an estimation problem. It's the way to estimate the answer by breaking it into chunks.
So we don't care about it.
No.
Okay, awesome.
Section 7,
I don't.
7, I think is Simpson's rule. So you should have gotten that for your derivative. So my integral, I'm doing it in terms of x, so I'm going to use my x values. So 1 to 2, square root of 1 plus 1 over x to the 4th dx. So this is where sometimes you get problems you cannot do. All right, there's no way for us to integrate that. Well, there's no easy way to integrate. There's always ways to actually do the integration with a lot more math. However, we're looking for an exact value of this length. We have the technology. So Simpson's rule actually allows you to break it down and to do it in chunks. So you're looking at each piece as you go and get closer and closer between 1 and 1.1 and 2. And depending on how many values you choose, you'll get that. So this is basically what Simpson's rule does. I'll show you because it's in the book anyway. So Simpson's rule basically allows us to break it down into chunks and plug the values in to get an actual value out. Okay. However, we've got technology, so we're going to use technology. So in Desmos, in the graphing calculator, you cannot do this in the scientific calculator. I don't know why they haven't put it in the scientific calculator yet, but it is in the graphing calculator. If you start typing in integral, it'll give you your integral symbol. Put your values in. So 1 to 2, square root 1 plus 1 over x to the 4th. And you have to put the dx at the end, and then it will give you the answer. Okay? So we have technology. Like, nobody is doing this out by hand anymore anywhere in the world. Like, no boss is ever going to make you do this out by hand. Yes. What was your question? Oh, okay. All right. So
So if we get something like that on a test, we just shove it in Desmos and call it.
Yeah. So that's what you would use. Okay. In essence, the calculator is doing Simpson's rule. It's got that stuff already programmed in the background to be able to do those calculations, just like how it estimates anything. It already has those calculations built into place to be able to do those types of things. So use them. So that would be our answer. When you get to a point where you just cannot do it, like the integral just doesn't work, like you can't do, we have no rules that are dealing with x to the negative 4th power. We have things dealing with squares and stuff like that, but not negative exponents. And if you try to do trig substitution, which you might have, if I'd given you this on a test like number 5, and you tried crazy things, you might have tried trig substitution. The problem is the square root wouldn't have worked out to clean itself up. And if you remember when we did trig substitution, all the square roots kind of eliminated themselves. In this one, it would, because you'd end up getting a trig function to a negative exponent, which would not disappear. So, yes. Yes, it's impossible to do.
Yeah, that's why I said I never learned the tangent of the
The element of tangent, yes.
broke it in half. Just like that.
Yeah, there's no way to do it. I'm giving people credit based on the work they did. So basically for that problem, I wanted to make sure that you knew that you had to do integration by parts. You did integration by parts correctly. You ended up getting something plus the integral of ln tangent x, if I remember right, was the actual end piece there. And you figured out that you can't do that. That's literally what I'm looking for in that problem.
I just had a TPL on that.
So, all right. So in this case, we wanted it's a definite integral, so we can do it in Desmos, so we can get the answer. If it wasn't a definite integral, you turn out and say I can't do this problem. Okay. Let's do some problems, because that's literally all I'm teaching you tonight. So now we get to do some problems. You guys are going to get kicked out of this one. I knew I saw this problem somewhere.
I can't.
Oh, I didn't switch over. Darn it. There you go.
That's not cool.
Can I show you what I did?
That was funny. No, we're not doing that problem. Actually, but in this case, that's why not the integral. We're not doing the integral of that. You have to square it and plug it back in and all that other stuff. But this one, it actually says use a computer. It literally says then compute the length using a computer. So, I just thought it was funny when I saw it there.
That's usually not.
Answer: nope, not doing it.
Doable. Can't do
No
it.
thanks.
Nope.
All right, let's do this one.
I have a screenshot of the text.
All right. Okay. Set up my integral. Yes, you have to use the table.
It's been a while.
That's why I chose this one. We don't have to rewrite this one. We can just so 2/3 times 3/2 1 plus x squared to the 1/2 times 2x.
Oh my goodness.
This is a great. Multiply by everything.
It's going to. This was out in front, so I just left that out in front. This goes down in front of that times the. It's all multiplication, so it doesn't really matter the order you put it in. Which we now can clean up because those are going to cancel itself out. And you end up with 2x 1 plus x squared to the 1/2.
Squared.
Well, yes, I haven't done that part yet. So remember chain rule comes up. So squaring that. So dy dx. Actually, I'm just going to do 1 plus it. 1 plus dy dx squared. So 1 plus 4x squared times 1 plus x squared. Which equals 1 plus 4x squared plus 4x to the 4th. All right, so that's just under the square root. So my integral is going to go from 0 to 1 of the square root of 4x squared, or 4x to the fourth, plus 4x squared plus 1 dx. Can't do substitution. So factor, try it. Yes.
How did you get +1 on the left side?
Because under the square root, it's 1 plus dy dx squared. In the arc length formula. So
Oh, yeah.
that's that. I just, instead of doing the squared and then doing the 1 afterwards, I just figured I would do it together, saving some space. Before I was doing this to square, and then I would add the 1 to it.
So I have dy dx squared
Which should be 4x squared plus times 1 plus x squared.
equals 4x squared times 1 plus x squared dx. I obviously did something wrong.
You got that?
That's what I just said.
That's right. I just distributed it.
Where'd you get the 1 from?
The 1 there. That's the one.
But if it's on, but there's a 1 on, there's 1 on one side and there's a 1 on the other side for what you got.
Okay, hold on.
Yeah,
First one, that doesn't need to be there.
no, that's wrong. I was
So-
about to erase that.
Distribute that.
Yeah.
And you'll have exactly what I have. Distribute your parentheses under your square root.
Can I factor this?
Yeah. Yeah.
1 squared plus 1 squared.
I don't understand why there's a.
All I did, that's the square root part. That's,
It looked like there was a.
I just, instead of doing, I just didn't write the square root a million times. But yeah, you have exactly what I have. You just wrote the square root. All right. This piece right here, you have to be able to factor that. So this is where, if you remember when we were looking at chapter 7.5 and we did the review for the test, what was the first thing they said to look at before even use substitution is algebraic manipulation. Factoring is one of those big things. We have a square root. We have something underneath it that doesn't look like it can be square rooted. See if you can factor it to possibly deal with that. In this case, I can't. That becomes 2x squared plus 1 squared. So now I'm just doing the integral of 2x squared plus 1 dx. So that's where that algebraic manipulation really comes into play. And why I still say in all my calculus classes, your mistakes aren't going to be calculus, they're going to be algebra. Because you would have got to that point and go, I have no clue what you want me to do. Yes.
So how are you able to recognize that something is factorable when it's like more than just like x squared plus something?
Well, so as long as they're multiples of 2, x to the fourth, x squared, x, x to the sixth, x to the third, they all work the exact same way as x squared plus x plus 1 or whatever it happens to be. So in that respect, this can be factored just like a regular quadratic cube. Now it's a matter of being able to recognize those perfect trinomials and things like that, where in this case, well, if I look at this one here, the square root of that is 2x squared. If I double it, I'm going to get the middle one, and the square root of 1 is 1. It kind of works out. It's like, unfortunately, it's one of those things that it's the practice and looking at those on a regular basis to be able to figure those things out, which I know is not as easy in the world to think about it. But you have to realize in the end that most of these problems, unless it specifically tells you to estimate, you should be able to do. So if you get to a point where it's like something doesn't make sense, go back and look at it, or email me and see if I screwed up something on the test. But in this situation, it should be able to be done. So, and that's why looking at factoring is probably the best way to go. Yeah.
So if it didn't factor into a perfect square,
You wouldn't be able to do this way. You'd have to do
Okay.
something else. And then it's possibly maybe you could do completing the square and using the trig substitution. Because we could do completing the square and trig substitution.
I don't know, complete square.
So that's another possible way to do it. But first thing, look for the easy answers first. And that's where that algebraic manipulation piece comes into play. All right, so we have now actually a very simple integral.
I almost wrote box in there.
What's the integral of 2x squared?
2x cubed over 3.
2x to the third over 3 plus what's the integral of it is x. And we're evaluating from 0 to 1. So I got 2/3 plus 1, which is plus 1. It's 5/3. There you go.
I'd be scared for a second. I was like, whoa.
So it's plus 1. That's what happens when my brain works faster than my pen. All right. What do we got? Let's see. Let's do. I like that one. Let's do that one. I've seen them 3 times now.
Skillet?
Mm-hmm.
Yeah.
Fox was last year with last kind of song.
Oh. I don't like that.
We don't have to do the chain rule for this one.
Yeah, I was gonna say, I think
Yeah,
I might prefer channel.
walk through the problem piece by piece. Believe it or not, this one's not nearly as complicated as it looks.
I feel like I just did some algebraic bullshit. Can you get this? Yeah, I'll do it. Let me know. 32 divided by 4 is 8, right?
If you write it that way, it might help you a little bit figuring out your derivatives.
Whoa. so I shouldn't. Okay. It's minus.
Yes.
Is that what you got? Well, I just have to take it. Oh my god, that's wrong.
Oh, it's not 1/4, and that's 1/2 in the middle.
Where's that one at?
The middle term when you when you FOIL. Yeah. You end up getting 1/4 and 1/4, which is why.
Half of the one.
What's 1 minus 1/2?
What's half?
1 minus 1/2.
Half.
Right. That's where that 1/2 came from. That's what happened to the 1.
No, I'd rather be cooked.
I've done no calculus. All I've done, I did some calculus. I did the derivative, so I lied. I was gonna say everyone in here I know can do that part.
I'm glad I'm not in there. Technically,
Oh, you could do the derivative too.
like maybe.
Really?
Not today.
I think we just multiplied it together.
Yeah, okay.
All right.
That's your fault.
One of those things I will tell you, this tends to come up a bunch, is things like that, where you have a positive exponent and a negative exponent, and then the middle doesn't have an exponent. They're perfect squares. 99% of the time, if you see that, it's a perfect square. Okay. And the symbol in the middle will be whatever symbol that is.
Will be whatever.
So if that was a minus, it would have been a minus.
He's good.
Yeah.
I don't know how did you get rid of the square root?
I haven't even done the square root yet.
Not there.
I've literally done everything under the square root. I haven't wrote the square root yet.
You're gonna lose it though, right? 'Cause you have to square
Yeah.
it. So-
Yeah, the square root's going to cancel itself out in a second. But I haven't even put the square root there. So technically, everything on this side is under the square root.
But I got,
So
I got 1/4 times y to the 6 plus y to the.
you forgot. Okay, so you did you when you foiled, what did you get?
I got y to the 6 minus y to the 0 minus y to the 0 plus y to the -6.
So
Because I did 1/2.
hold on. So we got 1/2.
Yeah.
Y to the third minus
Y to
1/2 y to the -3 squared. So
Yeah.
or times itself. Yeah, I know that's what he
Oh,
got.
that's 1. I thought y to the 0 was 0.
Nope.
Yep. All right, I get it now.
Okay. Yeah, because you should have gotten in the middle.
Yeah. You can go enroll in algebra 1.
It's okay. It's okay. And then again, minus 1/4 y to the 0, which is -1/2. And then the plus 1 is where the positive 1/2 comes from. All right, but yeah, everything on this side is in essence underneath that square root. So, and then, so if this is all under the square root and the square are going to cancel each other out. So my integral is from 1 to 2 of, what is it, 1/2? Yeah. 1/2 y to the third plus 1/2 y to the -3 dy. These ones are long because of all the algebra that you have to do just figure it out. So I actually really like this problem.
Whatever it is.
So for the integral, we get 1/2 times y to the 4th over 4 plus 1/2 y to the -2 over -2 from 1 to 2. So we'll clean this up a little bit. 1/8 y to the 4th minus 1/4 y to the -2. Actually, I'll get rid of my negative sign. So 2 to the 4th power is 16. So 16 over 8 minus 1 over 16. Minus 1/8 minus 1/4.
Do we leave it with that?
No,
16 is 200. Whoa. Yeah.
which ends up equaling 33 over 16.
Oh my goodness.
So if you just change them all, so we got 32 minus 1 minus 4 plus 8.
Wait.
Wait,
Where's that
32,
four come from?
6, not 32. I looked at that, then I did 32. 2 and 4. There we go, that's better. I did the first part at 16, and then I somehow 32 got stuck in my head. Which gives you the 33.
I thought that was real familiar to the first part of the question. It says 1/8 minus squared.
Well, yeah.
That's the different sign.
Yeah.
So we did all that math to change the sign?
Yeah.
Is that a consistent thing?
No.
that happens?
So you can't just like,
Skip all of it.
no, it doesn't always work that way. Be nice, but it does not always work that way. All right, one more problem.
Hey, I'll just go make that in the sheet metal lab down there. Give me like 20 minutes.
I haven't done an application problem yet,
I'm
and
just gonna make
I wanted to actually show you an application style problem.
28 inches like that. All right. Yeah.
All right,
Enough for days. I'll do it. 16 gauge, 32 gauge.
so they're giving you the equation for it. So if you think about this, this is actually something that really would have to be done. Like, you don't buy sheet metal already pre-curved and everything else. You literally have to do that. Right, you have to make the curve. So when you order it, you would have to order the correct length based on what you want it to be at the end. Well, yes. But in terms of arc length, that wouldn't matter. The gauge wouldn't change. So we want our panel to be 28 inches long. We want it to have a 2-inch high wave. So they gave us, be nice, the equation for it. So you do not have to do the algebra to figure that part out. Okay. We want the actual width of the original sheet of sheet metal, which means we want to know what that is, which is my arc length. Okay. So set up my integral.
How
Yes.
would we figure out the limits of?
So I want it to be how long? So 0 to 28.
So is that
Because remember, when we're looking at our integral, we're looking at the actual curve. So my curve is starting at 0 and going to 28.
we have to change the equation in the X to figure out like what?
It's already in terms of x.
No, sorry, because like 0 to 28, that'll we can that allows us to figure out how long to make it.
Yeah.
But to make it to figure out how thick to make it, don't you have to change it into terms of the other one?
We don't care about the thickness. We're not looking for.
It says it needs to be 2 inches high.
Right. So, okay. So this part right here,
Yeah.
they if you notice, it says verify the sine curve of the equation is this. they gave you the amplitude of the sine wave, and in essence, this is 2 sine waves. They gave you the period. You then would have had to figure out to verify that equation. They've done that for you. So you didn't have to actually use this to figure out the actual equation. That's the piece that you didn't have to actually worry about there.
But we still need to multiply the sine by. The sine is bounded from -1 to 1, so we have to multiply it. Oh, wait, no, that's 2 inches. Yeah, that's 2 units.
Yeah.
Ignore me.
You don't have to worry about it. All you need to worry about, this whole thing that gave you the equation. So figure out the arc length, that equation. If I wanted you to actually find that equation, we would use the 2. Yeah.
We got to square root of 1 minus pi over 7 cosine pi over 7 all that square.
You can't do it.
Oh, okay. Okay.
No, you can't do it.
Okay. Can we plug it in, right?
Yeah. You plug it. All right. You should get. And actually, a lot of these types of problems, a lot of the application problems, you just literally can't do because the equations are just too complicated for it.
So we got the.
Was it pi over 7x? So your derivative of that is that. Chain rule. Don't forget the chain rule. You need to use chain rule for this one.
Yeah.
Because there's a pi over 7 x inside. Happens to be the lesson I'm going to teach my Calc 1 class tomorrow. Yeah. You get to do chain rule tomorrow.
Aren't you so excited?
It's funny going back and forth between
What
Calc
time
1
is
and
that
Calc 2.
class?
9:30.
Might show up. Just to be like, I need a refresher.
Plugging it into my integral formula, my arc length formula, because we're going from 0 to 28. The 2, okay, I will explain where the 2 came from. What is the amplitude of a sine wave? Okay, so what is the range of a sine wave? No, what's the range? Not the domain, the range, the y values. The lowest sine wave, -1 to 1. So -1 to 1 is how big in inches? 2 inches. So it's just the sine. So the only thing you would actually have to figure out in this one with the 2 doesn't matter because the 2 is just telling you that's how from the bottom of the sine wave to the top of the sine wave is 2 inches, which is 1. So the period, and this length is 28, so that's how you get the pi x over 7 because it's 2 pi x over 14 because this is actually 2 waves. If you the way you look at it, it's 2 waves. So it's 2 pi x over 14, which is pi x over 7. That's the period. That's where that came from. So now we finally got rid of the 2. We're going from 0 to 28, and that's my equation. This cannot be done. You would use a computer to figure this one out. Okay, you would just type this one into Desmos and get the answer. So your answer ends up being approximately 29 inches long.
Okay. That's good.
So that's how long I'd order the sheet metal for.
Tomorrow.
You don't, because somebody else has done it.
Oh, you have.
Yeah.
I saw it. He was like, you were one of the-
Yeah. So here's what typically ends up happening in most of the fields. Because I worked at the tech schools for so long, like I've dealt with electricians and plumbers and HVAC, you name it, I've worked with. They all come up with tricks and things to make the things easier so they don't have to do the complex math. So if you're an electrical, you did Ohm's law, you did all these other things. These are quick little tricks so that they don't have to deal with the algebra and stuff afterwards. So when you're a master electrician or a master plumber or a master HVAC technician, like you've done it so long that you know things without even having to worry about doing it. The person who originally created those plans better have known how to do it and did it right. That's where your architects and your engineers and stuff come into play because they have to create this stuff originally to send out to the people who are actually working in the field to do that stuff. So no, your sheet metal person's never going to do this. However, the original engineer that did it, that's going to have to send the order off to get the panels made, had to have calculated this at some point. So, and they might have used a computer to do it. That's very possible. Now we have computers to do it, but understanding the process behind it's never a bad thing. Bye, guys. Go get some sleep, Bo.
Thank you. Sorry about